All right, hello everybody. Welcome to the first audio lecture we're going to do for experimental psychology. Just once again, I want to thank everybody for being flexible with all this stuff and to keep in communication with me if you have any issues with accessing these or issues with any of the content or anything. I'm going to try to do the best I can, just like we all are under less than ideal circumstances. But again, thanks for being flexible and please keep in touch. So I'm starting our unit here on inferential statistics. In this first video, I'm going to talk about hypothesis testing and power, things like that. And then in a second video, I'll talk about particular types of inferential statistical tests that we might run, including the types that are relevant for your projects, and then a little bit about probability to finish up that section. So to start off talking about inferential statistics, I think it's useful to compare them to the types of statistics we've already talked about. Remember, we talked about descriptive statistics earlier in the semester, and those were things that allowed us to obviously describe the data that we have. So those tend to be things like percentages, means, medians, modes, the shape and variability and types of distributions that we might have in the data that we get statistically after collecting data. You can compare these, though, with inferential statistics. Inferential statistics generally are using some of the descriptive statistics in combination to test our hypotheses. So descriptive statistics, you're just saying, 70% of people engage in some behavior, or there's a mean score of, 5.7 on a 10-point scale or something. Inferential statistics are about saying something about the context of those. Is that a significant difference from some other attitude, or is there an experimental manipulation that affects some outcome variable? So inferential statistics instead are using these distributions and trying to tell us if a result or difference is likely or not. The ones that you are all going to be using for your tests or for your studies because they are experimental and have categorical independent variables are t-tests and ANOVAs. But we'll talk a little bit about correlations and regressions as well. They have some of the same underlying math as t-tests and ANOVAs, but they're looking at relationships rather than actual group differences. But when we talk about inferential statistics, what we're trying to do is talk about things where we're making decisions about how our hypotheses. Do our data support our hypotheses or not, basically? So sometimes we might also be interested in just kind of predicting what's going on in a population. If you remember when I talked about statistics initially, I distinguish between a statistic, meaning something about a sample, and a parameter, meaning something about a population. So if you have a big enough sample, you can make an estimate about a parameter from your statistics, and you can make a judgment about how likely it is for that parameter. So think about when people are doing polling ahead of an election, and they're saying that 40% of people support this policy or this candidate with a sampling error of plus or minus 3. They're making a parameter estimation about the base level of support for that person or thing and telling you that there's some level of slippage in that estimation. What is a little more germane for our class, instead of that parameter estimation, because our samples are so small frequently in psychology that we're not able to say anything with much confidence about what the whole population is like. Instead, we're trying to say whether a difference or relationship is due to chance or not. Trying to say whether those differences are likely to be representative in a bigger population. So when doing frequentist hypothesis testing, which is what we will tend to do in this class using like p-values and significance testing, the big question you're trying to figure out is it probable that my results are due to chance? You want to minimize those possibilities that your results are due to chance and rather be confident that the differences you're observing between different groups are real, or that they represent some aspect of reality. And if you drew another sample from that same population, you would like to think that you'd find the same thing. So you're trying to reduce that likelihood that your results are due to chance. So remember, just to review what a hypothesis is, though you're all forming them at this point, hopefully you have a pretty good handle on what they are. But a hypothesis is just the statement of a relationship that you have predicted. And remember, it should be very, very specific, so you are saying exactly what would and would not support your hypothesis. It's also really important, especially as you're nearing the time where you're going to be thinking about testing your actual predictions yourselves and writing them up, that we don't use the language of proving in any hypothesis test, really, because we're just trying to minimize the chance that our results are just due to random chance, basically, and one study can be unreliable in any number of ways. We would never say that one hypothesis test proves our hypothesis, but instead we would say that it offers some kind of support if our findings were supported there. And if it did not support it, then we'd say our hypothesis was unsupported. One thing to remember about hypotheses too, is that we often think about them as just having one form where we predict our relationship. But actually there are two types of hypotheses that we're implicitly making whenever we make any prediction. And these two kind of paired up hypotheses, they should describe every possible outcome that we could see, and they should have no overlap whatsoever. So we don't want it to be the case that some of the results we find, we would never, that they would not characterize what we would observe. So they should be exhaustive and mutually exclusive. And what I mean by this is that the hypothesis that we generally are going to make, that we expect there's going to be a difference in our intelligence testing due to our stress conditions or something, that is what's known as the alternative hypothesis generally, that there is some kind of effect. The null hypothesis is kind of what you are, as a researcher, often hoping to avoid. The null hypothesis is just the case where there is no effect. So you can see how these things, they're simple and straightforward enough that they're exhaustive. There either is no effect or there is an effect, and they're mutually exclusive. There's nothing about them that shares any properties. There's no set of results that is going to show you that both of these things are true. It's going to either be one or the other based on how you set your level of confidence. So how you set that level of confidence is something that we call an alpha level. That's where you're basically setting the cutoff for what level of chance am I willing to tolerate that my results might be influenced by. So if you think about in this kind of first figure here, usually the alpha level that people set sort of as the default is an alpha level of 0.05. And if you think about hypothesis testing and how you're trying to get a p-value less than 0.05, this is where that 0.05 comes from. The alpha level is the degree of chance that you are willing to tolerate. And basically what it's saying is in this distribution of all possible outcomes for null results. These are null distributions that in the middle, there's no difference between two groups. Over here, there's some negative difference between two groups, and over here, there's some positive difference. We're willing to tolerate a 5% chance out of this whole distribution of 100% that our results are due to chance. So, it's 95% likely that our results are real, 5% likely that our results are not. But this 0.05 level is completely arbitrary, it's important to note. It's just kind of what we've all agreed on collectively. And you can be more stringent with your alpha level, especially if you're working with big sets of data. It is the case that your alpha level is just going to be small because you have lots and lots of people in your sample. So oftentimes it is useful to set your alpha level at 0.01 and say, I'm only going to tolerate a 1% chance that my results are just going to be due to random circumstance and error. And as we'll talk about when we get to replication and reproducibility toward the end of the course, there is a big movement in psychology to kind of get away from this 0.05 level, because maybe that is leading to inflated estimates of different effects, and move to 0.01 or even 0.005 as the new golden rule as far as psychology. When you're using a directional hypothesis, These two distributions here over on the left are the types of things that we tend to think about, that all of your error is concentrated in one end of your null distribution tail. But if you're using a non-directional hypothesis where you're just saying basically we think that there's some difference, then you're kind of agnostic about if it's less or more. So the alpha level gets separated into those two different tails under those circumstances. And for this reason, when you get to SPSS and you're testing your differences, SPSS by default gives you a non-directional p-value. So actually you need to cut your p-values in half because they're two-tailed, but Jenna and I will talk about that in different videos when we post more about SPSS. It's also important to note, though, that just because you're seeing a significant value somewhere, it's important to distinguish between what we mean in science when we say statistically significant and what we mean in just everyday conversation when we say the word significant. Statistically significant just means that it's unlikely that our results are due to chance according to that alpha level that we have chosen. It doesn't mean that the results actually matter. It just means that the size and direction of that effect are probably reliable. But I mean, if the finding that you are discovering is something like, people are half of a percentage point more likely to look up into the sky if they have just heard the word up in the last half hour, like, I don't know, does that matter? Is it actually significant? Probably not. So significant in the statistical sense doesn't actually mean meaningful. It has a very specific statistical meaning. That's important to remember. When you are doing these types of hypotheses testing too, it's also really important to remember different types of error that are involved. And by this, I don't mean like measurement error in the way that we've talked about it before. I mean like mistakes or accidents. So that alpha level that I talked about earlier is related to one of these types of errors. The alpha level that you choose, so often 0.05 or to new standards 0.005, this is the possibility basically that you are accepting that you might make a mistake in saying that there's an effect. Rejecting the null or rejecting the idea that there's no difference when there actually really is no difference. So the probability of a type 1 error, the probability that you're making that mistake, is equivalent to your alpha. So you're saying basically, I will take a 5% chance that I'm going to mistakenly say that there's a kind of effect. A different type of error that you can also make, that's sort of the opposite sort of error, is a type 2 error, failing to reject the null when it's actually false. And this is noted by a different proportion that I'll kind of explain in just a minute using some different distributions. But the probability that you make this opposite error, saying, oh, doesn't seem like there's any effect when there actually is an effect, that is a type 2 error. And the probability of that type of error is usually denoted by beta, a different Greek letter. And another thing just to mention up front, I'll kind of circle back to this again, but 1 minus beta is something that we call power. Power is, how much ability you have to detect a true effect when it exists, basically. And it kind of makes sense that your ability to detect a true effect when it exists is sort of inversely related to the likelihood that you're going to fail to notice those true effects. So these things have a connection that is really hard to pull apart. Okay, I think this figure also is a little bit more clear in some cases than talking about these things in a really abstract sense, right? You can think about the types of things you're observing and deciding in a statistical manner by this sort of 2x2 space. That in reality, so what is going on actually, truly in the real world, either the null hypothesis is true and there's no effect, or the null hypothesis is false and there is an effect, is not the same as the decision you're making as a researcher. As a researcher, you're trying to find out these things, but you're making a separate decision about, like, do I think there is an effect or not? So failing to reject the null hypothesis, saying, looks like there's no effect according to my data, or rejecting the null hypothesis, saying there is an effect according to my data, can be crossed with these things from reality. So you can see that when these things are crossed, there are good decisions, basically, and bad decisions. Those errors that I talked about are represented here, and those correct decisions are represented here. So the two types of correct decisions, there is no effect, the null hypothesis is true, and you notice that. You fail to reject the null and say there is no effect. That is a correct decision, that there's no effect. You might also make this other correct decision, that the null hypothesis is false, and you find that you think from your data the null hypothesis is false. Yep, another correct decision, that there is an effect, the null hypothesis is false. And remember that I said your ability to detect those effects when they really are true, remember that is power. And then you notice here, this would be represented by that 1 minus b, or 1 minus beta idea, and the corresponding idea up here is beta. That you're making that type of error. So you can see how these things are related in this chart. The other type of error, though, is that you reject the null and say there's an effect when there's really not. So this is that 5% chance, or 0.05, or half a percent chance you might be willing to take that you're making this type of error. And again, this is the other correct decision. So I think this is maybe more helpful once you kind of have the terms from this part of the slides to think about it in terms of this, and it makes it a little more concrete. When you're designing a study, though, what you're hoping to do is maximize the chance that you are making a correct decision rather than making one of these errors, a type 1 or type 2 error. You want to make these correct decisions. So when you're trying to do this, you are trying to make A as small as possible, but you also don't want to make it impossible for you to detect an effect. If you made your A, 0.00001, you might never reach that level of confidence. So we want to figure out how much error we can tolerate, but we don't want to be unreasonably small about it. And again, this 0.05 is an arbitrary decision that we all just kind of agree is a reasonable level. But it's also important to remember that the stricter we set alpha, if we make alpha smaller, then the chance of making those type 2 errors is bigger. So these things are kind of linked to, and let me show you some distributions that kind of explain why. So if you remember earlier, I was showing you those null distributions, that if we set our alpha at 0.05, 5% chance of seeing a result due to chance, let's say this is the distribution of possibilities when there is no effect. And here's our alpha, our 5% part of this distribution where we're willing to make a mistake. But that overlaps with the distribution of possibilities where there is really some kind of a difference. So if we think about these in tandem, this alpha level is related, in a sense, to this beta level. If you would move these one way or the other, you would inflate one while you deflate the other, basically. So here's one error, your type 1 error, where you're rejecting the null even when it's not true. Here is your type 2 error, where you are accepting the null when you actually do have a difference. There really is some kind of true difference between those different conditions. And here, in 1 minus b, is your power. These are all the real true differences that you might detect and correctly say that there is some kind of difference. But look at this 0.05 here. If you were to lower that to 0.01, that moves this threshold between retaining the null and rejecting the null over, and it inflates this area where you have the possibility of a type 2 error. So by minimizing type 1 errors, you're actually inflating the likelihood that you're making type 2 errors. So it can be really just kind of difficult to try to figure out which one of these priorities is more important. Is it worse if I make a mistake and say there's an effect when there's not? Well, if I reduce that, then I might miss something that's really there. So these things are inextricably linked. You can't move one without the other. this other idea that I mentioned, this idea of power, that you want to maximize your area where you're going to be able to detect a true effect. If you make your alpha smaller, that's going to shrink your area of power here too. It's going to make it more difficult for you to detect those real effects. So remember, I've talked about this 1 minus beta area that I just showed you. That is what power is represented by. And power, again, is the probability of rejecting the null when the null is really false, or saying there's an effect when there really is an effect. Because beta always has a value between 0 and 1, power also always has a value between 0 and 1, and you want to maximize that value. You want it to be closer to 1. And the higher power you have, the more likely you are to detect actual effects. Another thing that's important to remember is power is also affected by other things you're doing in your studies. If you just collect more data, your power is going to increase. So if you have 1 million participants, then you're going to have higher power to detect even a really small effect. But then again, remember, those effects might not be meaningful if you have 1 million people. So just remember, bigger sample sizes, more power. And when you have a particular sample size, like let's say 400 people, the type of effect that you're looking at changes your amount of power. So if you have a really big effect, your power to detect it with 400 people is going to be pretty high. But if you have a really small effect, your power to detect it might be more like, somewhere in the middle, like 0.5 or 0.6 to detect a really small effect with the same number of people. So there's a lot of calculations involved in these. We won't go into the specific equations in this class, but important to note that it's being more and more accepted today that you should do calculations of this before you actually run studies, and you should actually find out how much power you need to detect a particular effect rather than just collecting 200 participants and hoping that you have the right circumstances to detect that effect. All right, well, I'm going to end this part of the video here. Thank you for, again, tolerating the circumstances here, and I think this is working out, and we'll move on to talk about statistical test choice and what all the different tests do for us in the next video.